Right, hello guys, how are you today? Today we want to look at electricity and magnetism, but we are going to first focus on electricity in this video. Right, so if we can refer to the paper that I've pasted there, we know that in metals we have a certain type of bonding that is called metallic bonding. So metallic bonding is the type of bonding that is found in metals. So what happens in metals is this. You remember the structure of the atom. The structure of the atom is in such a way that, simplified structure, at the center of the atom we have protons and neutrons that make up what we call the nucleus. And then around the atom we have electrons that are constantly orbiting. We have something like that. So in an ordinary material, like maybe plastic or rubber, which is a non-metal, we have atoms like this. And then this is the positively charged nucleus. And then each atom has electrons that are revolving around it. So this is just a simplified diagram so that you can understand what we are saying here. So this represents a non-metal. This represents a non-metal. So what will be happening in a non-metal is that the electrons will be rotating around their particular atom. So these electrons are not able to move from point A to point B. This electron, for example, cannot move from point A to point B. It keeps on rotating around its particular nucleus. So because it cannot move from point A to point B, it means this material does not conduct electricity. Because to conduct electricity, electrons need to be able to move from one point to another. I hope that is okay there. But if we now compare it with the situation that happens in a metal, if I draw now what happens in a metal, in a metal we have the atoms here. Positively charged, positively charged, positively charged nucleus. It is positively charged because of the protons. So what happens now is we had an electron that was here. But this electron that was here, let me just indicate only one electron. The electron is revolving around this particular nucleus. It belongs to this atom number 1. But the nucleus of the neighboring atom, it is going to pull that electron. So this electron, instead of revolving around here, it is going to be pulled, so much so that it ends up in the middle there. So this happens everywhere throughout this material, and then we are going to end up having electrons all over. So this is called a sea of delocalized electrons. So this is what happens in a metal. So in a metal, the electrons do not belong to any particular atom, but they are delocalized. So they are found in the spaces between the atoms. So when that is the case, it means now these electrons are able to move from point X to point Y. So if an electron can move from point X to point Y, it carries charge. As an electron moves, it carries charge. And then when a charge is carried through a material, we conclude that the material is able to conduct electricity. So I hope you understand that. So it's a very special type of bonding that is found in metals called metallic bonding. So let us move on now. So it is what I wrote on the page there. If we can just look at the page. So we said electrons are not confined to one particular atom, but form a sea of delocalized electrons, as I explained there. So in electricity, there are 3 physical quantities that we need to explain. Very important physical quantities. The first physical quantity is called current. Electric current with the simple capital letter I. So what is electric current? It is the rate of flow of charge. So if they ask you to define current, you simply say current is the rate of flow of charge. When we say the rate of flow of charge, scientifically, what does that mean? The rate of flow of charge in simple terms is basically the speed at which charges are flowing through a circuit. So once we talk about rate, for us to talk about how fast or slow something is, it means we are measuring that something with respect to time. So once you see the word rate there, you need to know that we are referring to the time that it takes. All of us can run 100 meters, but you guys are young, maybe you can do it in 10-15 seconds. Maybe me, I can do it in 30 minutes, but I'm still running 100 meters. So it's not about finishing 100 meters, it's about finishing 100 meters in the shortest time. That's when we say you are the fastest. Are we okay there? All right, very good. So current is the rate of flow of charge. So when we say current is the rate of flow of charge, it means we can have a formula which says I is equal to Q over delta T, where I is the current, the electric current. It is measured in amperes, or we call them amps, and then for that we use capital letter A. Then Q is the charge that we are talking about, and charge is measured in coulombs. We know that from electrostatics. Then obviously delta T is the change in time, and the SI unit for that is the second. So we need to be measuring the time in seconds, which means if we are given time in minutes, we need to convert it to seconds before we can do any calculation. So based on that, we say the units are current, the units of current are amperes, or from the formula we can actually find that the units of current are coulombs per second, because we are saying coulombs divided by seconds. So let's do a simple calculation there. Let's say calculate the current when, let's say question 1.1, 5 coulombs pass through a circuit in 10 seconds. 1.2, 20 microcoulombs pass through the circuit, this time in 3 minutes. 1.3, let us say 8 nanocoulombs pass through a circuit in maybe 0.5 seconds. Then 1.4, let us say 4 millicoulombs pass through a circuit in, let us say, 2 hours. So right now, I want you to pause this video, and then after pausing the video, you do the calculations, and then let us see what you come up with. Then we do corrections a little bit later on. So I hope you guys have paused the video. We are continuing. Right, let's look at it now. So what you do here is, we are supposed to calculate the current, so we are using the formula. So let me just squeeze it here on top so that we can see it clearly. You can see it clearly. So we are going to do the first one together. Very simple. 1.1, I is equal to Q divided by delta T. So what is our Q? Our charge here is 5, and charge is measured in coulombs. So you need to check, are the units correct, because we need to use standard international units in our calculations. So 5 coulombs, it is already in coulombs, no problem there. Then I'll say 5 divided by the time. What is my time? 10 seconds. So it is already given in seconds. So if it is given in seconds, then I do not have a problem. I just have to divide already by 10. Then this is going to give me 0.5 amperes. That is how I calculate my current for 1.1. Very simple. You see that? Now, when we go to 1.2, this time we have a problem, because 1.2, we are asked to calculate the current, but our charge is given in what are called microcoulombs. These are very small charges, micro, nano, very, very small charges. So you need to know what the micro means. Micro is written like this. It is a funny U, so you write it like this. That is how we write micro. So I hope you guys can see that. So what do we do for 1.2? For 1.2, we do a very simple thing. We write the formula first. Our I is equal to Q divided by delta T, which is equal to, my charge is 20 microcoulombs. Micro means exponent -6. It means times 10 to the power of -6. So you need to know that whenever you see micro, you must know that we must say times 10 to the power of -6. That is what micro means. And then divided by the time. The time is 3 minutes. Are you okay? So if the time is 3 minutes, we can't use 3 minutes here because we are supposed to use the standard international units, which is the second. So we need to change those 3 minutes to seconds. So how do we do that? We know that each minute has 60 seconds. So if there are 3 minutes, it means it is going to be 3 multiplied by 60. Then we divide. You take a calculator and then you get your answer. I think you guys can do this. It's very simple. And then remember to write the units, amperes. When you go to 1.3, this is 8 nanocoulombs. So nano means times 10 to the power of -9. So you need to convert this to 8 times 10 to the power of -9 so that it can be coulombs. The time, we are not going to convert it because it is already in seconds. Is that okay? Then 1.4, it is 4 millicoulombs. Milli means times 10 to the power of -3. And then the 2 hours, you need to change them to seconds. Are we together there? So we know that 1 hour has 60 minutes and each minute has 60 seconds. So we need to say 2 multiplied by 60 multiplied by 60. Then we get the number of seconds there. Then we just basically divide. Are we together there? I can also just tell you that centi means times 10 to the power of -2. Kilo means times 10 to the power of +3. There are other topics where we are going to do calculations where we need to get into that in detail. So I hope we understand current. The faster the charge is, the higher the current. Why are we saying it is the rate of flow of charge? Because electrons are called charge carriers. Let me just write it there. Just write it somewhere here. Electrons are charge carriers. They carry charge. That is what it means. Electrons are charge carriers. So whenever electrons are moving, they carry charge. So the faster they move, the higher the current. If the electrons are moving slowly, then it means the current is low. But if they move faster, we say the current is higher. Are we together there? And then there was a scientist called Robert Millikan, an American scientist. He's the one who quantified the charge on an electron. So the charge on an electron, which we normally call QE, is equal to -1.6 times 10 to the power of -19 coulombs. So that is the charge on one electron. You need to remember that. And the charge on a proton is positive 1.6 times 10 to the power of -19, because remember, protons are positively charged. Ernest Rutherford, he proved that using an experiment, that the nucleus is positively charged. So it is because of those protons. Are we together there? So we understand now what current is. Then from current, we need to look at what is called the voltage. Voltage, capital letter V, it is the work done per unit charge. So in other words, if we have 2 points here, we have a point A and a point B, and then this is a conductor. It is a material that is able to conduct electricity. So when we are measuring the voltage, which we sometimes refer to as the potential difference, the potential difference of the voltage is the work done per unit charge. In other words, in order for us to move a charge from point A to point B, there is work that must be done. So the work that must be done for each and every charge is what we call voltage. and it is measured in volts, or it is measured in joules per coulomb, because the formula is V is equal to W over Q. It is the work done per unit charge, where W is the work done, and the work done is measured in joules, and then Q, we know that it is the charge, which is measured in coulombs, and then V is the voltage, which we measure in volts or joules per coulomb from the formula there. So I'm sure we understand what we are talking about. So again, there are calculations we can do here. We can do very simple calculations like what we did with current. So let us look at them. Let's call it question 2. Calculate the voltage when 2.1 500 joules is used to move 20 microcoulombs of charge through a circuit. Let's say we have something like that. 2.2, let us say 800 joules is used to move 4 coulombs of charge. Question 2.3, let us say 2 kilojoules is used to move 4 microcoulombs of charge. So it is again basically the same as we're doing there. So you can pause the video and then you do the calculations and then you see what you come up with. All right, very good. So now let's just look at 2.2. Let us do a solution to 2.2, just one of them. So we write the formula V is equal to W over Q. Then W is the work done. So what is the work done in question 2.2? It is 800. And the 800 is joules. So joules is the correct unit. Joules or joules, I don't know how you pronounce this. So that is the unit for energy. So it must be in joules. If it is kilojoules, then we cannot use kilojoules. We have to convert. And remember, I said kilo means times 10 to the power of positive 3. So here, the work done is 800 joules already. So it means I'm going to just substitute it as 800 divided by, what is the charge? The charge is 4. And then you take your calculator, you divide, then you're going to see that this gives you 200 volts. Are we together there? So basically, that is what we do with voltage. So you can just look at these questions and then they are very simple. You get them right. Now, moving on. So we have talked about two things so far. We've talked about voltage and we've talked about current. So there is a third quantity that we must look at, that is called resistance. So resistance, the symbol for resistance is capital letter R. So by definition, it is the opposition to the flow of electric current. It is the opposition to the flow of electric current. So in other words, when current is flowing, it is going to face some resistance, some opposition. So that opposition to the flow of electric current is what we call resistance. Then this resistance is affected by 4 factors. So there are 4 factors affecting resistance. So the 4 factors affecting resistance can be summed up with one formula there. Let me just write the formula down. The formula is R for resistance is equal to rho L over A. So this is a formula which sums up the factors that affect resistance. So the R there is the resistance, the L represents the length, the A represents the cross-sectional area, and this rho is spelled like this. You just write it here. This is rho from the Greek alphabet. It is the symbol for resistivity. I'm going to talk about that now. So let's look at the first factor, length. So length is represented by small letter L. So we say a resistance is directly proportional. Resistance is directly proportional to length. Very important here. What does this mean? When we say resistance is directly proportional to length, it means the longer the conductor, the higher the resistance. In other words, if I have two conductors, remember when you are comparing two things, for it to be a fair comparison, something must be the same. You must maintain something constant so that it can become a fair comparison. So let us say we have two conductors. We have conductor X and conductor Y. These are basically two wires. So what is the same here? If I look at my drawing correctly, I see that they have the same thickness. They have the same area. So at least I have something that is the same. The thickness is the same. The width is the same. The cross-sectional area is the same. So they have the same cross-sectional area. What is only differing is the length. So when I look at this, I see that conductor Y is longer than conductor X. So because this one is longer, it is going to have a higher resistance. So I can conclude to say that the resistance of conductor Y is greater than the resistance of conductor X. Why? Just because conductor Y is longer. So which means if you are transmitting electricity, the correct language we use when we talk about electricity is transmitting electricity. We don't transport electricity, we transmit it. So when you are transmitting electricity, let us say from Johannesburg to Cape Town, it means you are going to use long lines. So when you use those long lines, they are going to cause an increase in the resistance. So we are going to compensate for that as we transmit electricity. When we go to the topic of electricity, we are going to talk about how they compensate for that high resistance, which comes out as a result of the very long conductors that they use. So that is one factor which affects resistance. So we understand how length affects the resistance. Then the second factor is cross-sectional area. Factor number 2 is called cross-sectional area. Cross-sectional area A. And then let us write what is happening there. The cross-sectional area, okay, let me start with the word resistance. The resistance is inversely proportional to the cross-sectional area. The resistance is inversely proportional to the cross-sectional area. What does this mean? Let's talk about what this means. This means that the thicker the conductor, the lower the resistance. So what do we mean? Let's put it into perspective. Let us say I have two conductors again. This time I have conductor X and I have conductor Y. This is now my X and this is now my Y. Or maybe to avoid confusion, let's use different letters. Let's call them conductor C and conductor D. So these are two wires. So which one is going to have a higher resistance? Which one is going to have a lower resistance? Remember we said, when you are comparing two things, for it to be a fair comparison, it means something there must be the same. So here, whatever I maintain the same, the length, you can see that my two conductors, I attempted to ensure that they are of the same length. So they have the same length, but you can see that conductor D is thicker. So if the conductor is thicker, it means current has more spaces to pass through. Are we together there?